Hey guys, in this video I'll talk to you about the life of a star. We'll talk about things such as the birth of a star, the life cycle, and the eventual fate of a star, and factors determining its destiny. This video is just going to be a brief overview. I'm not going to go into too much scientific detail, in that I'm not going to discuss things such as the chemical structure, the rotation, the nuclear fusion process, and how energy is transported from the core to the surface. I'll just briefly touch upon some of these, but the main purpose of this video is that I will explain the paths taken by each star and the main reasons for it. So, just a few notes before I begin. A star is a massive ball of plasma which is formed in highly dense clouds that contract under gravity. The stars undergo radical changes during its lifetime, and this happens in sequences. There are many factors which influences its fate, but ultimately what it comes down to is its mass, and this is a key point. The lifetime of a star can range from a few million years to trillions of years, but then you may say that the universe isn't trillions of years old, so how do we really know what processes a star goes through? And this comes down to extensive computer modeling. Scientists and astronomers can look into the night sky using telescopes and very advanced scientific techniques. They can determine the mass, the chemical composition, luminosity, surface temperature, etc. And they're able to use this information and determine how far a star is into its life and what type of a star it is. And they've created sort of a map for this in the early 20th century, known as the Hertzsprung-Russell diagram, and we'll come to this. Also, just for comparative purposes, in this table you can see how much more massive the Sun is compared to the Earth. Apparently you can fit over 1 million Earths into the Sun, and our Sun compared to other stars is quite a mid-range star. So to begin, let's look at this star formation process. Stars are formed in highly dense clouds known as giant molecular clouds. These giant molecular clouds are made up of matter, which typically have mass equivalent to 6,000 suns, which we call 6,000 solar masses, and they span across over 100 light years. So it's really highly dense clouds. And what happens is these break up into smaller pieces, with the collapsing gas releasing gravitational potential energy as heat, and as the temperature and pressure increases, it will condense into a rotating sphere of superhot gas known as a protostar, as illustrated in this wonderful diagram. And typically for a star like our Sun, it would have taken about 100,000 years to form a protostar. And just one more point to make is that the British physicist Sir James Jeans considered the detail of star formation in detail. He was able to show that a cloud or parts of a giant molecular cloud would contract very swiftly, and he derived this formula for calculating the mass and the size of a cloud. It would have to be as a function of its density and temperature before gravitational contraction would begin, and this critical mass is known as the Jeans mass. So let's look at dwarf stars. Dwarf stars have a mass, or protostars, which have a mass typically of 8% solar mass or less. And what happens in these is that brown dwarfs have gravitational contraction which doesn't heat the protostar very effectively, and the temperature in the core doesn't get high enough for fusion to occur. And so what happens is it reaches a point where electrons are packed so close that gravity cannot really contract it any further, and creates a new sort of pressure known as quantum electron degeneracy pressure. And since gravity cannot contract any further, what it results in is a failed star. And so simply we call this a brown dwarf, which cools off by radiating away its thermal energy. Next, let's look at red dwarfs. Red dwarfs have a mass typically of less than 40% solar mass. Here, it has a core temperature which is low, but high enough for it to start the nuclear fusion process, whereby hydrogen is fused together to create helium. What happens in these red dwarfs is that energy is transported from the core, where the fusion process is happening, and it goes to the surface mainly through convection, rather than radiation, which you find in larger stars. And because of this, it burns a larger proportion of hydrogen compared to larger stars, and so it's typically lasts longer than larger stars. And funnily, what you find is that lower mass red dwarfs have a longer lifespan. So a star typically of the size of 10% of our sun would continue burning for 10 trillion years, compared to, or is it about 10 billion years for our sun. So that's quite amazing. And the main point is that this is because of the way it transports energy from the core to the surface. Red dwarfs are the most common type of star in our galaxy, or at least in the neighborhood of our sun. The nearest star to the sun is Proxima Centauri, which is a red dwarf, and 20 of the next 30 nearest stars are red dwarf stars. But due to their low luminosity, we cannot see red dwarf stars with the naked eye. So you have to use a telescope to be able to see these. Let's go on to main sequence stars. Stars will spend about 90% of their lifetime fusing hydrogen to produce helium in the core, which is of really high temperature and really high pressure. What will happen is the proportion of helium in the star will of course start to increase as hydrogen fuses to create helium, and to maintain this rate of nuclear fusion, the star will slowly increase in temperature and luminosity. Our sun is at that stage at the moment. It's a main sequence star. It is estimated that our sun will burn for 10 billion years, and currently it is almost halfway there into that cycle. It's about 4.5 billion years into that cycle, and I guess the amount of energy that a star can generate through this nuclear fusion of hydrogen is limited by the amount of hydrogen fuel that can be consumed at the core. And this diagram just illustrates sort of a sun-like star, where outside of the core you have the radiation zone, and outside of that you have the convection zone. And I guess this is important because, as I said before, smaller stars have just the convection process of transporting energy from the core to the surface, compared to our sun, which has a radiation zone and then a convection zone. But then in even larger stars, it's opposite to our sun, where you have the convection process in the middle and the radiative transportation of energy on the outside. And I guess this is key because it determines how long the star will last for because of this. Next, let's go on to giant stars. And what happens is that eventually, when a star uses up all its hydrogen in the core, it will develop this radiative core, as I mentioned before. And subsequently, what will happen is it will start to burn hydrogen in a shell surrounding the core. and giant stars typically have radius of about 10 to 100 times greater than the Sun, and luminosity is much more than the Sun. It can go up to about 10,000 times greater than the Sun. Main sequence stars of a quarter of the mass of the Sun or less will not become a giant star. If it is greater than a quarter of a quarter solar mass, then the core will contract, heat up, the shell will expand and cool, and the radius will then increase drastically, forming a red giant. Even more massive stars, such as stars greater than 8 solar masses, will use up all the hydrogen and start fusing other compounds to create other metals in the core, usually up to about carbon, and these will be even more luminous, and these are known as supergiants or hypergiants. Eventually, these giants will become a white dwarf, which is composed of oxygen and neon. If it's over 9 solar masses on the main sequence, then what will happen is the core will collapse and it will create a supernova. And after this supernova, it will form neutron stars, or it can even go on to become a black hole. And so you can see that the mass is really important in determining how a star will end up. And just for comparative purposes, the VY Canis Majoris is a star located in the Canis Major constellation. This is a red hypergiant. You can see how much larger it is compared to our Sun in that diagram. As I mentioned before, the Hertzsprung-Russell diagram is typically used by scientists to determine where a star is in its life cycle. And this diagram is a plot that was made in the early 20th century after analyzing thousands of stars, and it's a plot of luminosity or absolute magnitude against the spectral type. And spectral type is a sort of a classification type for a star. It's sort of a way of saying the temperature of a star. And as you can see, the main band going across like an S shape is the main sequence, where stars will spend most of their life. So I guess a good way to summarize this is to look at this. And this is a chart or diagram from the NASA website. It shows you a very good way the evolution of a star, depending on the mass of the protostar. So, just to conclude, the initial mass of the star is the main factor to determine the evolutionary path of a star, and it can take many paths. But of course, there are a lot of other factors to determine this, which you can go into so much more detail, and it can get a lot more complicated if a star has a nearby companion, such as a binary star system. And of course, I guess this could be for another video. Hope you enjoyed this video and learned from it. Thanks for watching.